All right, so this is the screencast for some of the multiple choice questions from topic 4 and 9. And what we're going to be doing is just looking through the right answers on the key, but also looking at why those answers are the correct answers. We're doing this for our e-learning because we don't have class, and it works a lot better to do it this way, I think, than trying to ask every little question in the group video when we're using Google Meetups or something like that. Anyway, this is what we're going to do. So the first point I'd like to make is this gets a little blurry at times, hard to see. So what I would do is have this document in front of you or this PDF open at the same time so that as I'm going through things, you can check what's happening. I'll try to go slow enough, but I need to go fast because I have a limit on how long this video can be. And so I'll go in order so that you can skip ahead if you're looking for a particular question. So here we go, page 1, and we're looking at number 3. It asks which one of the following graphs would produce a straight line. So straight line means we're going to take this equation, which really comes from T equals 1 over F equals 2 pi squared m over k from 9.1. This is looking at the mass on a spring. So our y equals mx analogy would be y equals some mx. So the y-axis, definitely we would want to graph 1 over f. So that works out nicely. And then here we would say this is equal to 2 pi over root k times the square root of m, where this would be your m and your x, and the plus b is a 0 here. So we'd expect it to go through the origin if you plotted root m. So b is our answer there. Looking at the next one, 21, graph P shows the displacement at one point in a wave as it varies with time. So this is over time. Graph Q shows the displacement in the same wave varies with distance along the wave at one particular time. So here we have distance at a given moment in time. So clearly we have two very different ideas here. They look similar, but this one is how a particular particle is moving as the wave goes by in time. That's what this one is. And then this one is, oh, there's the whole wave, and we're taking a picture of it just at that particular moment in time, the displacement distance graph. So question asks, which one of the following expression would give the speed of the wave? So the speed of the wave here would be the wavelength over the period. And so if we think about needing the wavelength over the period, and if we look at for wavelength, clearly this is going to be the wavelength, and this is going to be the period. And so either one of these distances is half of the wavelength, and the time difference here is half of the period. So it looks to me like if we're after velocity, which is the wavelength over the period, we could use half of the wavelength over half of the period also. And so it looks to me like C would work nicely. If we look at D as another possibility, it's x3 minus x1, and you might be tempted to use x3 minus x1 because that is the actual wavelength. But if you took that, you'd need to divide by the actual period, which would have to be 2 times t2 minus t1. So notice that t2 minus t1 is half of the period, so that means we need to use half of a wavelength, and that's why we're not using the entire x3 minus x1. And that's why C is the right answer, since it only gives half of the wavelength and half of the period to be equal to the velocity, which is the speed of the wave, which is why we get C for 21. For 22, as this thing fights to focus, pretty annoying, similar type questions. And these graphing questions are typically what's hardest for students, and so spending some extra time and making sure you're really getting on what's happening here will help. So the two graphs, we have two different graphs. They're both with a time axis. of an individual displacement of two waves as they pass through the same point. So this is the time as you go along on one particular wave as it goes through a point, and this is another one as it goes through that point. So this is asking about superposition and how these things will add up over time. And let's take a look at the question asked. So the displacement of the resulting wave at time t is going to be, this one is going to say to go up x1, and this one is going to say to go down this negative x2. So obviously B is the answer that we want here, where this one's saying go down by an x2 amount, and this is saying go up by an x1 amount. So that's 22, and the answer is indeed B. All right, let's see what we get with 23. It looks like we have the first harmonic of a closed. So we know that the wavelength here is 2 times the length. This is half of a wavelength that they've shown here, which is nice. This is a standing wave. And this is showing at one point in time, and then this is showing half of a period later, and it's moving back and forth between these points, and we'll go through the straight in the middle. String is stretched between two fixed points. It's plucked as a guitar string, and it's vibrating at its fundamental. Which one of the following expression gives the frequencies of the other possible modes of vibration that have an antinode at the center? So that's tricky, where the number n in each expression is all of the possible integers. So this frequency that we have here is the fundamental. We know that closed will have all of the possible n's, but we need to know the ones that will have a node in the middle. So I guess I can do this right on top of this. So obviously the second harmonic is going to have a node in the middle. I'm trying to remember, what do we want? Which one of the following expressions gives the frequency of other possible vibrations that have an antinode in the center? So 1 we want, 2 we do not want, 3 it looks like we want, 4 will have a node there. So it looks like we want all the odd values for n. And so how can we create odd values? And that's B, because we have the even numbers minus 1 give us the odd numbers. So that's nice. 24. So this is a pretty tough topic 4 question, actually, wasn't it? Anyway, here we have, looks like it's going to be a Doppler shift question for number 24. And it looks like a particle is moving to the right in all of these. And we're looking at if the particle is the source, the observer. So let's see what it says here. Wavefronts produced by a source of sound, constant frequency, as it moves at a constant speed towards O, and it must be going less than the speed of sound. Because if it was going faster than the speed of sound, it would be in front of the waves that it's making. So A is obviously the right answer here. I think C and D have some sort of weird non-circular thing. It's definitely going to be circular. And this one is if the source isn't moving. So pretty easy question, a little weird. 24 is indeed supposed to be A. 25, we're asked, the waves from two light sources meet at a point, which condition is essential for interference to be observed. And so we would want to have constant phase between them, and we also want to have constant wavelength. We want the wavelength to be the same, and we want to have, so we say monochromatic and coherent. And so the best answer here that I see is constant phase between the waves, which looks pretty good for A being the right answer to 25. 26, we have the double slit experiment again. That's what this was showing. Right, we've seen that one. In any case, it looks like at P we're going to have a dark or bright spot. Let's see what we have here. Produces bright and dark fringes on a screen. Region point is indicated below the screen. The light of the two slits has equal amplitude at reaching point P. Which one of the following gives the change, if any, of the appearance of the bright and dark fringes when the amplitude from one slit is reduced? So this is a tricky thinking question where we have to think about, to have destructive interference, the the one that's canceling out of phase needs to have the same amplitude as the one that's positive in order to truly cancel. So we won't be able to cancel it if they have different amplitudes. So one of them is reduced. So at the brightest spots, let's say we had